Guys, so this is my how-to video for Adventure 3 Quest 2, where I will be solving question 7.32. Now, in this problem, we have an array of 10 silicon chips. Each are a length of 10 millimeters on a side and is insulated on one surface and cooled on the opposite surface by atmospheric air in parallel flow. When in use, the same electrical power is dissipated in each chip, maintaining a uniform heat flux over the entire cooled surface. So we have a uniform heat flux on the top here, caused by the air, and all the other sides here are insulated. Now, if the temperature of the chip can't exceed 80 C, or the max temperature of the chip is going to be 80 degrees C, we want to find the maximum allowable power per chip. And then after we find that, we're going to look for the maximum allowable power if we're using turbulent. If we have turbulent flow over the top, there's a turbulent promoter at the boundary layer of the leading edge, so here. And then a simple question, if it's asking if we would prefer if the orientation of the chips is normal or parallel to the airflow. Now, in summary, we have these constants given. We're assuming steady state, constant properties, laminar flow, and constant heat flux. Now, we are going to validate our third assumption here to get laminar flow. But the way that the question is phrased, we can start by assuming that. And for the properties that we're finding, I'm going to be using air at 300 Kelvin. At table A4 in the appendix. And of course, we're going to find the max power in each chip, the max power if the flow is turbulent, and if it's better for normal or parallel flow. In order to validate our laminar flow assumption, we're going to use the Reynolds number with this equation here. And we have all the variables for that, so I solve this to get that my Reynolds number is 2.52 times 10 to the 5, which is less than 5 times 10 to the 5, so we have laminar flow. Now, because we know that there's laminar flow and constant heat flux, we can use this equation for the Nusselt number, where we have the Nusselt number is equal to 0.453 times Reynolds number to the 1/2 power times the Prandtl number to the 1/3 power. And we know the Nusselt number is also equal to HL over KF. Solving for H in this equation, we get that H is equal to 53.28. And we can calculate the power dissipated using the equation for convection, where I get that Qmax, assuming a surface temperature of the maximum 80 degrees C, is equal to 0.3 watts. Now, if turbulent flow, then we are no longer able to use this correlation of Nusselt number. And instead, we're using this equation, which was found in the textbook, where the Nusselt number is equal to 0.0308 Reynolds number to the power of 4/5 times Prandtl number to the power of 1/3. And we follow the same steps. So we get H is equal to 151.16. And that is a Qmax of 0.85 watts. Now, the last part is asking if it's preferable to orient the array normal instead of parallel to the flow. And in that case, it would be better to orient normal to the flow, because each of the chips would have the least interrupted air wicking away heat. And that's my solution for question 7.32.